The video today is regarding microscopic urinalysis examination, and we're just going to go over some of the final touches to summarize all the important aspects of microscopic urinalysis. The goals of this video today are to describe when we should be performing a microscopic urinalysis, contrast various microscopy techniques, review important sediment, classify abnormal crystals, and discuss urinary disorders. In general, a microscopic urinalysis should be performed when any of your dipstick results indicate a positive protein, positive blood, positive leukocytes, or positive nitrite test. Remember that we have a commercial system that we used in lab called the COVA system that helps to facilitate microscopic analysis, making it faster and easier to perform. There are 4 key microscopy techniques used in routine urinalysis in the lab. The one you're most familiar with is most likely the bright field microscopy, which is what we use in lab, and it's the simplest when you have light shining up through the specimen and you're looking at it from above. Bright field is good for stained specimens and specimens that have a pigment to them. As you can see here, this fatty cast has some sort of pigmentation. There's an oval fat body off to the right. Red cells and the like are also usually identifiable in bright field microscopy. The catch is that things that are generally transparent or translucent, like a hyaline cast or mucus thread, unless you have the light setting correct, it's going to be hard to visualize. So it is commonly used, but it does have its downfalls. It's better when you're looking at a stained specimen, in this case, using bright field microscopy. The second most common technique used in the lab is phase contrast, and it's very similar to bright field microscopy in that you can use primarily an unstained specimen, but it does give you greater brightness and definition of the specimens because it changes the light phases slightly so that you can have better contrast and see the edges a little bit better, especially of things that are unstained, things that are transparent, as well as smaller internal structures. It isn't often or always used in a lab, but you will see it every once in a while. The next type of microscopy used in the lab is interference contrast, or sometimes called differential interference contrast microscopy. Now, it is not routinely used because it's more expensive, but what you get with interference contrast microscopy is you get a more three-dimensional picture of what you're looking at. It's usually used on unstained specimens, as you can see here, and it gives you a really good contrast between the elements of the specimen and the surrounding fluid. Last but not least is polarizing microscopy, in which you're applying a filter to the light so that the light that's shining through the specimen is all traveling in the same plane. This is used primarily to help identify objects such as oval fat bodies or fatty casts, because under polarizing light, as you've heard before, they will produce what's known as the Maltese cross formation, and that's indicative of fat in the urine. Also, starch granules tend to produce a pattern like this, and so it helps us to identify what we're seeing a little bit more. Just a reminder that when we're staining sediment, we use what the classical stain is called Sternheimer-Malbin stain, and it's a combination of crystal violet and safranin, and those of you who have had microbiology will be familiar with those two stains. It's considered a supravital stain because it's used for living tissues taken from the body. Now, commercially, we're familiar with it under the names of SETI stain or COVA stain. When we define sediment, we use particular words to describe it, and one of those words we use is the word formed element. Basically, what a formed element is going to be describing is either a cell, a crystal, or a cast, something that has a very defined shape. This is a reminder that if you don't remember what casts are made of, review the TAM horsefall protein, which was discussed in your microscopy videos at the beginning of the semester or in your book. We also use the words organized or unorganized to describe sediment. And in general, organized sediment is usually biological, so that would be more like squamous cells, versus unorganized sediment are things like crystals, or in particular amorphous crystals that don't always necessarily have a set shape. Don't forget that on your first exam, there will be some visual sediment identification. There will be pictures on the exam, and you will have to list what sediment element they might be. We covered this material in the Lab 1 video lectures and in Labs 1 and 2. I've listed the objects that you need to know in the objectives, so be sure to go back and study them. Also listed on the objectives are topics that were discussed in the video lectures earlier, such as what crystals are abnormal and in what pH they form. So you should review that as well. Speaking of urine crystals, there's a couple important words we need to tie together in terms of crystal formation and how they affect the kidney. You know that crystals can take on a lot of different shapes. And when you have a high amount of a particular chemical, the crystallization process happens and forms the crystals. These crystals can clump together and form much larger structures known as uroliths, literally urinary stone. Lith means stone. And as you can see in the pictures, they can be pretty large and they can be pretty sharp and pretty painful. If they are within the kidney, we can also call them renal calculi, basically kidney stones. Calculi is plural for calculus, so if there's only one, it'd be a renal calculus. And as you can see in the image, they can be lodged in all sorts of parts within the kidney itself, and they can be pretty big again. And because they're so large and they can be very sharp on the edges and take up a lot of space, they can result in kidney damage or renal damage. Because as they travel through the kidney, maybe through the glomerulus, they can rip up the walls there, rip up the walls of the calyces, of the ureters, as well as potentially the urethra, depending on the size. So there can be some pretty serious kidney damage caused by the presence of these crystals and the formation of these uroliths. People who have had kidney stones definitely can attest to the pain that they can cause. Note that as well as metabolic waste products such as uric acid or leucine that can cause crystal formation, there are a series of medications or things such as radiographic dye used in different tests in the lab or in the hospital, that can also cause formation of renal calculi. A few of them are listed in your objectives, and it would be a good idea for you to check out those extra substances to be aware of that can cause urine calculi formation. Last but not least, we're going to discuss common contaminants that can be in a microscopic urinalysis exam. These things include stuff like starch, potentially from gloves, fibers from clothing, air bubbles, oil from the microscope, glass, precipitated stain, pollen, or even feces. All of these things can potentially get into the urine and confuse the person doing the microscopy if they're not well versed in different elements. So for example, here up in the upper right, we have some starch granules that look very similar to potentially amorphous uric acid crystals, for example. We have a fiber or maybe a mucus thread that is hard to differentiate. And then we also have this pollen grain, which, believe it or not, can get into the urine. And it sort of looks like Mickey Mouse, but it definitely also looks like something that could be maybe yeast-like, bacterial in origin, and can confound and confuse the tech that's doing the microscopic exam. So be aware that there are many times when this can happen, and that you need to, if you're questioning something, look it up or ask, and not just guess. So this sums up our microscopic finishing touches. Make sure to review your objective sheet and prepare for your exam next week. If you have any questions, you know how to get a hold of me.